Welcome back. So on this part of the lecture, we're going to be seeing how kinetics relates to nuclear reactions. And we're going to be doing that by studying the half-life of radioactive material. And by doing that, we're going to be able to use radioactivity as a way to calculate the age of objects. And we're going to see that if we know the initial concentration, we know the rate constant, we know the time, we can calculate how much of the substance is going to remain or how much activity is going to remain. When I say activity, I'm referring to the amount of decay that happens, how many disintegrations per second are happening, how many atoms are breaking apart, and so on. So talking about the kinetics of radioactive decay, the first thing that you have to put on your mind is that all of them are going to be first orders. So rate equals K, the concentration or whatever we're measuring, to the first, right? And if this is first order, then your half-life is going to be 0.693 divided by K. Let's double check that number later. And we also know that the integrated law for first order will apply, where you can measure the initial amount, the remaining amount, the rate constant, and the time required to go from the initial to whatever remains. And you can express it like this also, same formula. So quick refresher about half-life. If I start with a mass of 10, half-life would be when all that has gone down to 5. So that would be right there. And the time required for that to happen, that's going to be your half-life. So it's the time required for something to go down to half of the original. It could be an amount, it could be radioactivity, whatever we're making. So that's where we are right now, dealing with the radioactivity, being first order, and so on. So once more, this is how you measure your half-life. So that would be the formula that we use for half-life. So if you know your half-life, then you can calculate the rate constant, right? And remember, half-life is the time required for half of a radionuclide to decay. And here are several half-life values for different isotopes. So uranium-238 is going to be 4.5 times to the 9 years. So we're basically saying that it's going to take over 4 billion years for 5 grams of uranium to go down to 2.5. So that's a lot of years, a billion years. But for example, iodine, 0.0222 years, which is basically some few minutes, is how much it's going to take for half of this iodine to go down to, to half of it. So this table is important because it gives you the half-life, and those values are what goes in here, and that would allow you to calculate your rate constant, right? And we can use these features to measure how old something is. For example, we use a lot of carbon-14 because this is the way carbon-14 works. The protons that are in the atmosphere are affected by the UV light. Because of that, they are transformed into neutrons. Most of our atmosphere, the majority of the air around us is nitrogen, so those neutrons are going to bombard the nitrogen on the atmosphere transforming or transmutating the nitrogen into carbon 14 and one proton. So that carbon 14 is going to be on the atmosphere combined with carbon 12, which is the most abundant. And as long as the conditions are the same, the ratio between carbon 12 and carbon 14 is a permanent ratio for animals and plants that are breeding or that are using basically plants that are using the carbon dioxide. So when that carbon 14 mixed with the oxygen, it's going to create carbon dioxide, which the plants are going to use. And as long as the plants are alive, they are consuming that from the atmosphere, where the carbon 14 and the carbon 12 have a fixed ratio or proportionality. So carbon dioxide in, oxygen out. And when the animals eat the plants, they are consuming also the same ratio. However, the moment the animal or the plant dies, then that constant exchange of consuming the proper ratio of carbon 12 and carbon 14 stops. And the carbon 14 is unstable more than the 12, and it begins to decay. So we can measure how much carbon 14 remains compared to what the standard is, and that tells you how long the living organism or the objects has been around without having an exchange of the carbon of the atmosphere. Basically, whatever carbon they contained on their structure, when they die, that begins decaying without any replenishment from the fresh carbon dioxide. So based on that, we can calculate how old something is. So because of the half-life of carbon, so carbon 14 have a half-life of 5,700 years. Because of that, the most you can calculate is something that is as old as 50,000 years. So if you're using carbon 14, the oldest you're going to be able to detect is 50,000 years, because after 50,000 years, the radioactivity of the carbon 14 that remains is so small that you cannot even measure it. So if you want to measure something older than that, like a rock, then you have to use uranium, because uranium have over 4 billion years half-life. So you can measure a lot more with that. So the uranium decays super slow compared with the carbon 14. So how are we going to integrate that into the kinetics? Well, we're going to be measuring radioactivity, and radioactivity tends to be measured in becquerels or curie. A becquerel is basically one atom breaking apart for every second. A curie is a number that involves a lot more, because atoms, we have billions and billions and billions of them, right? So a curie is a unit that captures more on one shot. So a curie is going to be 3.7 10 to the 10 disintegrations, or in another word, 3.7 10 to the 10 becquerels is going to be equal to 1 curie. So that's how many disintegrations per second happens in a curie or a becquerel. So basically, just keep in mind that these are units of measuring radioactive decay. So let's do a problem like this. So we have an ancient skull. So we know this is something old. And at this particular moment, the moment it was found, the carbon decay rate is 0.85 disintegrations per minute. So that's the present. That's how fast the carbon is decaying. So how old is the skull? How can we find that? Well, you have to know that as long as the organism is alive, the carbon 14 that is getting from the atmosphere is 15.3 disintegration. So this is the standard. The normal is that's how many disintegrations you're gonna get from carbon 14 as long as you're getting brand new carbon 14. The moment you die, whatever is on your body is going to continue decaying without any replenishment. And for this particular skull, the disintegrations are down to zero point 0.5 disintegrations per minute. So the question is, how old is this skull? Well, you know this is radioactive decay. So you know it follows first order reactions. So if you use the integrated law for first order reaction, which you're used to see like this, so the last time you were exposed to this, that's the way it used to look. But those brackets are concentrations. So we're not dealing with concentrations anymore. On this particular case, we're measuring activity. So on this particular case, we're measuring activity. So what you're measuring is the original, the initial activity versus the activity at whatever time we're talking about. So that's given by this. So you're looking for the time. So you're looking for how old it is. So the time. So the initial activity, that's gonna be 15.3. So 15.3 disintegration is the initial activity. The moment the skull was found, the activity was down to 0.85. So that's the activity at the given time, 0.85. So the natural logarithm of 0.85 equals minus the rate constant times the natural logarithm of 15.3. So we got a problem here. We still have two unknowns. The one we're looking for is this one. So we need to know the rate constant. So how can we know the rate constant? Well, you know that the formula for half-life equals 0.693 over the rate constant. So the rate constant is going to be 0.693 over the half-life, and the half-life is 5730 years. So this will allow you do the calculation here, that will give you your rate constant, you plug it in here, and all you have to do is solve for the time, which you already know how to do because we did a lot of this on chapter 13 or 14, if I remember right. So by using the half-life formula, you can find the rate constant by knowing which one is the initial, excuse me, which one is the initial activity and which one is the remaining activity, or how many grams you began with, how many grams you have left now. You can then use first order kinetics to find out how old this particular skull is. So make sure you review this. Make sure you review the kinetics knowledge that you already have, and then you can take it from there. So with that said, this is a better, a more organized way of solving this problem. And this is how old it's going to be. 24,000 years, which is good because we know that we cannot do anything more than 50,000 years with carbon 14. So with that said, you should be able to do this problem. Here is a table with the required half-life that you may need to find the rate constant. And with that, now you know how to use kinetics, to use radioactivity to your advantage, to be able to date or predict radioactivity and all that kind of stuff in terms of how active something remains and so on. So until the next time, when we will go a little bit deeper, and we're gonna start talking about fission and fusion, and we're also gonna see why a nuclear bomb has so much power. Why it's important that when we try to get away from fossil fuels, why it's important that we truly understand nuclear energy, and where is our future as a species in terms of fusion energy. So that's what we're talking about on the next chapter. So until the next one, when we will talk about those, see you soon.